Hello, my name is Hyman. I'm a professor of both mathematics and mathematics education at the University of Michigan, and I'm going to speak today about connection-oriented mathematical thinking. So, like many of you, I'm concerned with the performance of mathematics education in this country. Of course, issues of equity and social justice have a lot to do with that, but I also want to focus some attention on the goals of our curriculum itself. One of the premises of this presentation is that mathematical thinking is the highest leveraged and at the same time the least developed goal of our curriculum. And within that, making mathematical connections is a key resource in mathematical thinking, but it too is largely underdeveloped. And to provide opportunities for this, it's important to design instruction to explicitly cultivate what I call connection-oriented mathematical thinking. Now, there are a lot of sort of technical terms I've used here, and I will be unpacking what they mean in the course of the presentation next. So first of all, what is mathematical thinking and why do we care about it? We don't see people thinking, but we do see what they do when they're doing mathematics. And so what I want to list is a few of the mathematical thinking practices, the kinds of things people do when they're doing math. Next. So things like asking questions. Next. Making sense of problems and persevering in solving them. Next. Looking for and using patterns and structure. This is very important. All these are pretty big ideas, but they're kind of summary descriptions. Next. Constructing, evaluating, and comparing mathematical representations and models. For example, models of real-world situations. Seeking and using mathematical connections. And that's the theme I want to focus on primarily in this presentation. Next. Conjecturing, justifying and proving claims and conjectures. For example, the NCTM standards in 2000 argued that proving in mathematics should be a learning objective K through 12, which was pretty radical kind of suggestion, but nonetheless, most of our students experience proof for the first time, maybe in a high school geometry course. Listening critically to and learning from other people's ideas. And both parts of that are very important. Next. And finally, working collaboratively as well as individually. Next. So contrast this with what you see in our curriculum materials and in our tests. Next. For example, next. In the Michigan curriculum, there are 75 pages on facts and procedures and 3 pages only on thinking practices. Next. Similarly for the Common Core. Next. On the NAEP, the items that call for high-level mathematical thinking, or at least come close to it, are the ones that elicit the lowest levels of student performance on the NAEP. Next. And the same is true of other standardized tests. Next. This is both a reflection of the emphases in the curriculum, and in turn, high-stakes testing drives the shape of the curriculum. Unsurprisingly, teachers will teach to the test. Next. So now let me turn attention to mathematical connections. What are they and why are they important? Next. The first thing I want to emphasize is that more important than how much you know is how well networked is what you do know. Next. So well-networked means that the components of one knowledge are linked by many deep connections. Next. This is a feature prominent in much of current AI research, for example, in connection with neural nets. Next. A fundamental kind of connection is sameness or equivalence. When mathematics is full of cases where we call two different things by the same name. Next. For example, here you see several arithmetic expressions and a shaded area model that are all equivalent representations because they represent the same number on the number line. This is important because, for example, when we want to add fractions with unlike denominators, we could replace the fractions by fractions with the same denominator. Similarly, when we want to do multi-digit subtraction, for example, 52 minus 17, we can write 52, which in place value is 5 tens plus 2 ones, equivalently as 4 tens and 12 ones, which explains what's happening in the common subtraction algorithm to avoid subtracting a large number from a smaller one. An algebraic equation transformed using reversible arithmetic operations yields an equivalent equation. In particular, the two have the same solution space. So these basic connections about equivalence are not typically made explicit. When students learn about numerical equations, for example, they rarely see that these are simply statements that two arithmetic expressions have the same numerical value. But the notion of equivalence is much broader than linking different kinds of arithmetic or algebraic expressions. And I want to give you an example in discussing equivalence of mathematical problems, another kind of connection. So consider the following two mathematical problems. What would it mean to say that they are equivalent, or in fact the same problem in some sense? Next. So problem A, 3 people run a race. What are all the possible outcomes, first, second, and third, assuming that there are no ties? Problem B, in the 3 by 3 grid square, what are all the ways of coloring 3 of the 9 cells blue so that there's a blue cell in each row and in each column? For example, here you see a coloring of 3 of the 9 cells. So what does it mean to say that these two problems are mathematically the same or equivalent? Well, on the one hand, each of the problems has 6 solutions, but that's hardly enough to claim that the two problems are the same. More importantly, one can intrinsically match their solution spaces. For example, if we imagine in the colored square, grid square, that the columns of the square are the running lanes of the 3 runners, and that the blue cells represent the relative positions of the 3 runners at the finish of the race, then we see that this represents an outcome of the race, first, second, and third. And so we get an exact matching of the solution space of the colored square problem with the solution space of the 3-way race. Next. So this is what I just described to you. Next. Abstractly, we can say that both of these problems are really about the set of permutations of 3 objects. Next. Seeing and using this kind of connection is related to what cognitive psychologists call transfer, and something I'll say a little more about later. Next. So what does it take to design instruction to cultivate this connection-oriented mathematical thinking? Next. For one thing, the skills and disposition to make connections requires supportive instruction. Next. The first comment is that connection making is not a generic competency. It doesn't make sense to say someone is, in general terms, a good connection maker. One may do it well in sports, for example, but not in math, or vice versa. Next. By connection-oriented mathematical thinking, I mean the disposition to seek and to use mathematical connections, and having the skills and the sensibility to do so. Next. To cultivate this connection-oriented mathematical thinking requires purposeful instructional design and dedicated resources, notably time. Yes, connect. In mathematics, a common mode of both learning and doing mathematics is problem solving. Next. So a promising and organic approach to stage tasks that support students to look for connections among different mathematical problems. So I'm going to describe two instructional formats, design formats for this kind of work. Next. The two designs both are intended for collaborative small group work, and that is enacted perhaps over several days, at least several lessons. Next. The students are given a small set of problems, say listed as A, B, C, etc. Next. In the connection network format, the first of these, students are asked to sort the problems into groups. Next. They put letters in the same group if the problems are mathematically the same. I put that in quotes because I've not defined that. And what this means at first is to be decided and explained by the students themselves. For problems that are not the same, but still substantially related mathematically, draw a line connecting the problem groups and with the thickness of the line expressing the strength of the relation. Then each group presents the solution to this task is actually a connection network relating the grouping and the links between the different groups of problems. And this has to be accompanied with an explanation of the justifications for all the decisions made in constructing the network. Finally, you want to allow for a full discussion of the differences in the different groups' networks in this process. So to give you a feel for this, let me give you an example of a connection network problem set. So the first two problems, A and B, are the two problems we've already discussed. Problem C is this. From afar, you see three children on a merry-go-round. What are all the different orders in which you see them? Left, middle, and right as the merry-go-round turns. Problem D, what are the symmetries of an equilateral triangle? Problem E, what are all the three-digit numbers you can make with the digits 1, 2, and 3, using each one only once? No, go back, please. So the problem here, the task for the students is to group these problems so that you put together in a single group those which are mathematically the same problem. But if they're not equivalent but still related, then you make a line of appropriate thickness connecting those two problem groups. So here is a plausible connection network appropriate to this list of problems. Next. So notice here that we've collected into a single group problems A, B, and E. Now, we've already seen the equivalence of A and B, and it's fairly easy to see that problem E is equivalent to all possible permutations of the digits 1, 2, and 3. But you may ask, why are C and D not included in that group, but nonetheless linked? For example, in problem D, a symmetry of an equilateral triangle is determined by what it does to the three vertices, for example, and therefore you can represent each symmetry by a permutation of the three vertices. And in fact, in this problem set, you get all 6 of the possible permutations. On the other hand, what distinguishes it from the other problems is that it's not a priori clear that you get all possible such permutations. Similarly, when in problem C, as the merry-go-round turns, you see lots of versions of which student is on the left, which in the middle, and which on the right. And in fact, you get all 6 of the possible arrangements of them. So they all give the same number of solutions, but in the case of C and D, and for very different reasons, it's not a priori clear that you get all possible permutations. Now, to students, it may not be so convincing, the basis for this exclusion. And so what I asked them to do is to make up a new version of this problem set with the number 3 replaced by 4. So for example, and they do this without difficulty. So they have, for example, 4 people running a race, or a 4x4 grid square, or 4 children on a merry-go-round, or what are the symmetries of a square instead of an equilateral triangle? And what are the 4-digit numbers you can make with 1, 2, 3, and 4? So then I asked them, that seems like a fairly innocent adjustment in the problem formulation, but then when they do the connection network, they discover that in fact C and D, A, B, and C continue to present all the 4 factorial, which is 24 permutations of 4 things, whereas for problem D, they see that the only symmetries of the square are the 4 rotations together with the 4 reflections, altogether 8 instead of 24. And for problem C is a much more complicated geometric problem with only 12, not 24 solutions. So this is a kind of demonstrates some of the richness of this kind of instructional activity. Next. The second format is what I call the common structure format. And in this case, the students are given a set of problems which are told are mathematically the same. And their task is the following. So they're asked to find and describe one mathematical structure that underlies each of the problems, and to explain how that structure is expressed in each of the problems. Next. I do not try to define for them what I mean by structure, but leave it to the students to find and describe one in each problem set, and to support them in doing so. Next. Of course, the problem sets need to be carefully constructed for this test to be feasible. And in fact, it's quite a challenge to the instructor to make such problem sets. Next. And for this test to be interesting and educative, one would want some of the problems to seem, at least at first sight, to be unrelated to the other problems. Next. So to illustrate what's going on in this format, let me show you a couple of problems from a 5-problem common structure problem set. Next. Next. So in problem A, I have a barrel of red wine and you have a cup of green tea. Next. I put a teaspoon of my wine into your cup of tea. Next. Then you take a teaspoon from the mixture in your teacup and put it back into my wine barrel. Next. So now, which is more, the wine in the teacup or the tea in the wine barrel? So that's problem A. Problem B, the 2 diagonals of a trapezoid divide the trapezoid into 4 triangles. Next. What is the relationship of the areas of the 2 triangles containing the non-parallel sides of the trapezoid? Next. So to see what's going on in this fairly technical statement, you can see the picture, and what it's basically asking you about this trapezoid is the relationship between the area of the blue triangle and the green triangle. Next. So this involves looking for deep structure in the problems. Next. First of all, I think you will agree that these 2 problems seem at first sight to be totally unrelated. They belong even to possibly different parts of mathematics. Moreover, one might well be able to solve each of these problems separately, still without discerning any connection between them. Next. So what's the point of finding out how they're mathematically connected if you can solve them independently without noticing that? Next. It requires to see the connection, it requires that you find and describe the deep mathematical structure that the problems have in common, which is far from obvious. Next. This contrasts with transfer theory and cognitive psychology, which posits that if you know how to solve problem A or problem B, then you should be able to mobilize that knowledge to help solve the other problem, the other mathematically similar problem. Next. But this rarely happens because most students do not even see the connection between the problems, much less use that connection to transport one solution to the next. Seeing this connection would convey a much deeper level of mathematical understanding than the two problem solutions alone would provide, which is why such connection making is a high leverage learning goal, as well as being a challenging and frankly, a fun activity. But we have no right to expect such connection making if we don't teach it, which is my main point. I think that these ideas merit further research and development, and I want to thank you for your attention. First of all, let me thank you, those who are attending, for attending this session. I'm very happy to be here, and I've presented some ideas, which I've spent a lot of time thinking lately, and I would be very happy to get your feedback and to answer any questions that you may have. How do these ideas look in K3? So I'll mention one example I know even from pre-kindergarten and preschool that I learned from a session run by Bethany Riddle Johnson. So the children were playing with pattern blocks. So they were, the researcher was interacting with a 4-year-old girl. This is before any mathematics instruction. And they were looked at a pattern formed with squares, triangles, and the pattern was square, square, triangle, square, square, triangle, and a repetition of that. And then they asked the little girl, can you make this pattern? And she was able to do this pretty quickly. And then they showed a part of the pattern and asked her what block comes next. And she was also able to do that. But then they gave her some new materials like circles and hexagons, and asked her, "Can you make the same pattern with those materials?" So she thought for a while, and then she made a pattern that looked like circle, circle, hexagon, circle, circle, hexagon, etc., which was interesting. And then the really interesting question to my mind was, can you explain why that's the same pattern? So this is, again, this question about when are things mathematically the same? Because they're not, circles and hexagons are not the same as the squares and triangles. So she had to think for a while about that. And then finally she said, same, same, different. Same, same, different. So to me, that was an example of exactly what I'm trying to do. First of all, that a pattern is really the same as what I mean, an example of what I mean by a structure. And so saying that these are the same pattern means that there's a common structure underlying both of them. With a little more mathematical training, we would say, well, that's an AAB pattern. But we have a name for it, AAB. And this 4-year-old girl didn't have that language available. So she had, first of all, she had to see and understand the common structure. she had to give it a name and to explain the sense in which they were the same. They both, the correspondence between same, different, a repetition of two things, and then a new thing, and then again the repetition. So in the common structure format, the idea is that the task for the student is, first of all, to find the structure that's common between them, to give it a name, and then not necessarily describe it abstractly, but explain how that idea is present in exactly the same way in both of the two problems.